Hello world, we're live practicing problem solving. LeetCode medium level. There is a problem we picked. Let me share the screen. So I have a red pencil that will help me work on this problem. Clock. Let's look at the description. So problem 875, Koko eating bananas. Koko loves to eat bananas. That makes sense. There are n piles of bananas with the ith pile has pile I bananas. Piles, okay, that makes sense. The guards have gone and will come back in H hours. Okay, so we have piles of bananas and we have H hours. Koko can decide her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from that pile. If the pile has less than K bananas. Oh, so there is this K. The pile has less. She eats all of them instead and will not eat any more bananas during this hour. Okay. Koko likes to eat slowly, but still wants to finish eating all the bananas before the guards return. Return the minimum integer K. Bananas per hour. Speed. Return the minimum integer K, so minimum speed such that she can eat all the bananas within H hours. Okay, so within that number of hours is, wow, up to, well, hours is at least, well, okay, piles, there is at least one pile and 10 to 4. Piles is, okay, and then hours is, wow, 10 billion. Oh, billion, up to a billion, yeah. That each pile can be up to 8 billion. So that's piles length. Well, yes, each pile, yeah. No, the number of piles, yeah. Number of piles is that. Okay. So we need to return that minimum speed because she likes to eat slow, yeah. The minimum speed at which she can eat all the bananas within this number of hours. So let's say we have piles 3, okay, these 5 piles, and we have 8 hours. So 8 bananas at 4 bananas per hour. Let's look at that example. So how this will work is, well, that one will take 1 hours. So 1, this one will take 2, and she eats all of them instead and will not eat anymore during that hour. If the pile is less, then keep. What happens if there is more? We'll see. That's what I'm trying to understand. So that is also 2, because at the speed of 4, yeah, that will also 2, and that will be 3. Because, so that seems to be, the answer. Oops. Which is 8 hours. So within 8 hours, yeah, if we go to 5 hours, we can do that. But can we do it with 3? Can we do that with 3 hours? We can test it, yeah. So for 3 hours, we'll need, if we test it for 3, we'll need 1, 2, but here we'll need 3 hours. Here we'll need 4 hours. So that is more than the limit. And it seems like we could just, yeah, so first I'm trying, it looks like, yeah, it looks like, yeah, let's take example 2 as well, just to clarify, to double check. Yeah, so so at speed 30, we'll have 1, 1, 1, 1, and 1. Okay, but if we have less than speed 30, it will be more than 5. Well, it looks like the hours, yeah, you need at least 1 hour to take care of at least 1 pile. Okay, so that's kind of the rule. So for our left is gonna be length of files, our left boundary of the search. Our right boundary of the search should be what? So the K, the speed, it's probably the maximum. Like here, it's 30. If the speed could be very slow, very slow. It depends on the number of hours. If there is like, yeah, it could be. But that's what we're gonna find out. What should we take? Should we take like 1 billion as the maximum? 1 billion. Yeah. Well, yeah, because any pile can be 1 billion at max. So we can take maximum the billion, or if we take the number of hours that we have, there is at least the hours is at least the number of piles, but there is, let's say there is twice as much hours as the piles. Can the speed, well, there is this number of piles, number of hours. In this case, they're equal. Yeah, but they could be equal, but there could be like so much more bananas in each one, and then we will need to consider the speed of at least the maximum one here. So we can, I guess, we can use the maximum value as the maximum value as our, is the maximum value relevant? Probably, yeah. But what I'm thinking is, even if we take R at the billion, it's not that much. There is not that many steps of division to get from there is like, the billion is like 30 steps. So yeah, I guess it's a sort of a viable. We could optimize it, but we can do it later. The thing is, we want to check. Yeah, because what we're looking for is anything that within the number of hours is good. So we want to move from that. We want to search Or we can search from the hours. We can find the speed that is too slow. Yeah, because speed. The faster speed will keep us within the limit of hours. Now that when we find the speed that requires more hours than our allocated time. Yeah. So I'm thinking how to move these 2 pointers. Essentially, we will need to go for, we'll have a function that evaluates the time we need. But for left, let's start with less than right. And our guess is left plus right minus left 2. Now we'll run the function. Or this time, or this guess is time will get well, we can pretty much just do it here on the spot. What we need to do, so we'll say, okay, this is at this speed. Go over, because we'll need to pass this data files. Yeah, we can do it time should take the files should take k and should return, that's the function, return an integer. So what it does, it goes over files. And it's going to count the hours. So we're going to say v divided by k v divided by k, which is gonna be like 1 billion divided by 3. No, 3 by k, which is +1. Yeah, so count plus, I think that's the formula that should give us So there is at least 1 hour plus, yeah, so, and then return count. And that should give us, So now let's say we now have the guess of how many hours and it needs. And by the way, this time complexity is length of piles, and we will need to do that log n times, log h times, yeah, which is about 30, up to 30. Not too bad. So I think, yeah, if that's good of time complexity, yeah, 10 to the power of 5 essentially the time complexity, which should be good then. Now, binary search. So if guess what it looks like is there is this good number of hours, or the speed within the hours. Now the speed, there is this time, and if the time is 0, then we'll have h somewhere. Oops. And then we'll have the n. So that's the time, the allocated time, and at certain speed will be within that time, but at slower speed will jump out of that time. If we are within the time, yeah, and we want to know where we should be approaching because we want to find the minimum speed. Yeah, the minimum speed is here. Because essentially, the smaller the speed, the more time we need. So we need to find the minimum speed at which we just so essentially it will be going here, yeah, because if the speed is should we call it K? Well, k is considered the speed here, yeah. We're sending m as our guess, and we were getting some k is what? We're getting, oh, that's the time. That's the time. No, that's the, yeah, the hours. We're getting the time. So if that time is should we start? Yeah, let's see if we can. If the time is smaller than hours, so is less. Because if we are still, if and by the way, we could have the same time with different speeds. So if it's if the time is less or equal, oh yeah, we need to go when the time is above. So when the speed is so small, we don't have enough time. We need to find that smallest speed when we're out and add one more banana to it. It should be in, yeah. So if time, yeah, I'm reviewing binary search, and I'm trying to understand which, yeah, I'm trying to pick the range where we're good, which one we're good. Because we want to move quickly through that when the time is too fast. When we're good. When the speed is too fast. My intuition suggests we should go, yeah, if time is smaller or equal at the speed, then h, my guess is we should move the speed one up. And else, if the time is bigger, if the time is, yeah, if speed is not enough, actually it's m plus 1. That's what I wanted to say. We should hit that m. That's what my intuition suggests. And by the way, we need to return that m. So we return So at some point they will merge, and we need to return L. My intuition suggests this this could be the solution. It's somewhat unexpected. It's what are we missing? Oh, piles. Yeah, we invalid. What? Integer and float. Oh. What? Length of files is integer, and that is float? Let me get you the billion. I didn't know that. I didn't know it was a float. It returns a billion. It looks like it returns a billion all the time. So so we are counting the medium L plus R minus R minus L by 2. So we run at that speed. What will that return? Like that will give us something like 500 million. And at that speed, we'll still need like 4 hours. And 4 hours will be smaller. So L jumps up. And when 4 hours is bigger, M jumps up like to 500 mil. So we, L, yeah, it's wrong direction. Yeah, so the speed, we pick up the speed. We need to slow down then. If the hours, if the time is, if we are well within the time, we need to actually slow down. Yeah, so if we are well within the time, we need to slow down. And we are well within the time. Then we move the right of the speed. Yeah, I think it's like that. Yay, we got at least one right, but these are a bit off. So they go 1 point higher than, so the speed is 1 point higher than, well, it could be then that, but it could be, oh, we're running out of, this one loops over. Yeah, okay. Okay, so this seems to be, or could be, wrong answer at 17. Okay, this could be, but it's so there's one pile. Well, this is where I need to practice more to kind of get, because when I get a bit more confident. Oh, hey. When we get a bit more confident with the binary search basics, then we'll be able to we'll be more comfortable with juggling those twists when you have this function that like goes the opposite way, and essentially yeah, so it's expecting 1, but there is, yeah, it's expecting 2, but, or what is it? Oh, wait a second. Yeah, it's expecting 2, and we're giving it 1. So it needs 2 hours, or it, wait a second. Oh, yeah. So we have this number of hours and the speed of 2 hours, 2 bananas per hour. Yeah, we need that speed, not 1 banana per hour. So yeah, we need like to be a bit more confident about this. I need to practice this binary search a bit more. Oh, this runs out. Oh no, yes, this runs out because yeah, because because there is a logic which will work, but I don't think this should work because I think this will run forever. Yeah. So yeah, I guess to figure out it, because it's gonna take time to actually fix, to like what's the problem, like why in this case it goes okay, 1 hour is enough, it says, but the reality is it's not enough. You need 2 hours, the speed, I mean, you need 2 hour, two bananas per hour speed to actually solve this. So, yeah. So I would say, because I already tried playing with the binary search, and there's like several parameters here. So just randomly, I don't want to just randomly play with them, which is what I've kind of been doing this, just tweaking and seeing what works. Sometimes that might be a viable approach, but I feel it's not like the best engineering approach. You should understand like why. Yeah, so when these two pointers merge, we should be out. And it goes out, and because that's the mechanics of it. We reduce the search space. That's the speed. Yeah, we say, okay, well, our search space of the speed of the minimum speed is we're looking for the minimum speed at which we can still have all the bananas eaten. What is speed? So we're saying, okay, this gas gave us enough time. Let's reduce the speed to our gas and a little more, right? So essentially that means if we were at the minimum time, we would jump out and a little more. So in that direction, we go +1. If we are, that's here. Yeah. If we are somewhere here, if it's not enough time, if time is out of the range, yeah, then okay, we need to speed up. But we just say, okay, that gas, let's just move to that gas. Let's move our left pointer. So essentially, what's confusing here, I think, is with speed. Our left pointer and right pointer are, we need to fix our diagram. And that would be the opposite, We need to, the speed will go up. Will go down. The time will go down as we increase the speed. Yeah. So the logic will work like that. Yeah. If our gas, if we didn't have enough, if time is smaller, then we move the right -1. Yeah. Go like -1. Go m-1. Yeah. So let's say we were somewhere here. So we go like, let's move our right here. If m is here, we'll say, okay, right, and one more. And right now we're giving a little less and one more. So what that will do at some point, if we are on the left will just jump on the M. So as we go closer to our target, what will happen is eventually right will jump on L. That's what's going to happen. M always picks the right one. And right will jump on M. Runs out of time. Yeah, so right on L. Yeah, because and let's say we have the situation where L is here, because L never jumps above the height. L will stay here. So at some point, that's what we want to happen. We want a right to jump on L, and yeah, we want L to forever go close to H, but never above. But in this edge case, we have a situation where the speed is not even valid speed. Yeah, we have the speed 1. How will that work? Because what our maybe it's our formula here. Let's see. We'll have this value. We'll divide it by k. If we divide it by 1, k is this guess speed. So with a billion, it will always give us just 1 hour. Oh, wait a second. Yeah, what happens when there is just one pile? So count as 0. With this 500 million, it will give us 1 hour. So, which is very fast. Oh no, wait a second. Wait a second. So we get V is this. V divided by, it will give us 1. So count is 1 and returns 1. So at that speed, it will take just 1 hour. Yeah, and we have many more hours. So the time is much less. So our right, our right will jump to this half a bill. Then it will be jumping. Yeah, it will be jumping half a bill. Yeah, then it will be jumping to this number. Yes, speed at mm-hmm. Yeah, I'm trying to fix that. Um, mm, I'm trying. I see. Okay. Let's try to follow that. So, with half a bill is just 1 hour. So, um, yeah. So the time. Oh, that's what's confusing. Yeah, the time with that speed is just 1 hour. Okay. Yeah, when the speed is this high, yeah, the time is just 1 hour. Okay, that means we can move somewhere here. Yeah, plus and minus 1. Then we'll run again. I'll run again, and it will become yeah, when the speed is this. When the speed is so this piles this bananas yeah, when it but we have one less. It looks like we have the case is we have the pile is one more banana, so we need 2 bananas. So the time is this hours, and okay, even let's say we come at some point, we'll get like to this is like still this is that speed is what? Okay, 300 million bananas. And one less banana, one less number of hours. So when that number, yeah, at the next step, I'm looking at our function. Yeah, when our our k was 500. And then our k becomes smaller. Then our k becomes smaller. In the next step, when we reduce the speed by half plus 1, and then we reduce it again by half, it's like 250-ish. And that will produce at least 1 plus 1. The speed will be 2. And the speed, oh, wait a second. The count will be 2, the hours will be 2. Okay, the 2 hours, not the speed, yeah, the hours will be 2. 2 hours is still much smaller, so R will move. So yeah, it's a bit confusing, but yeah. But hours will move, the speed will move when we get to the, let's say we have 10 hour, we'll get to the speed at which, yeah, so it will move. I'm looking for some milestones here. Milestones. I'm looking for some milestones. Yeah, tracing this algorithm is a bit, because this is like reverse. Yeah, as we decrease the speed, and at some point we'll get to the speed that's equal. Yeah, we already passed that. It's still like 1 hour. And then we need to go like, we'll need to get to the point where the speed is. Yeah, if the speed is, right can move, but the left one cannot move, or the medium. So right will be doing this division. Well, right will be moving. What will happen at speed of 1? What will happen at speed of 10? Like speed of 10, for this case, we'll have, like, the time will be 10 times smaller. This one. Because we'll divide this by 10. So the time will be like this. And we'll compare it with age. Time will be still smaller, and we'll move to half of it. We'll be moving and moving. And we'll be reducing the speed. But wait a second, the speed of 10 will be this big. At speed of 5, maybe 1/5, at speed of 4. So at speed of 2 will be speed of 2. It will be half of it plus 1. So it will still be much smaller. And it will left will be on 0. So left will be on speed of by the way, when left is 0, when speed is initiate. How do we initiate? Oh no, left is not a 0. Geez, left is length of pile, so it's 1. Okay, so left is 1. R is 2. What happens? R left 1. Ooh, that is 1. M is 1 then. Plus 1, so M is 2. We always jump on. M is 2. Oh, it will try to. Trying to will be smaller. R will become 1. They will meet, and that's what happens. Yeah. We need 2, so that's okay. So there is a bug, and it's one of those binary search tricks, or little details that I should master. So I'll work on that. But overall, I think we're very close. And I think it was a good practice. So thank you for watching, like and subscribe, and we'll see you in the next video.